Pop quiz? If I release a bowling ball from my chin, will it ever hit me on the way back? Yes or no? The answer is no. Without an extra push, it can't rise higher than where it started, so it stops just short. That's energy conservation at work. Now, let's zoom out and see how energy diagrams explain this. In this video, you'll learn how to read energy diagrams U versus X, find stable, unstable, or neutral equilibria, and use the total energy line, or E, to spot turning points and where motion is fastest. First, the basics. An energy diagram plots potential energy U of X against position X. Think of a terrain of hills and valleys. The important contrast: the horizontal axis is position, not time. For conservative forces, we can choose U of X, so the total mechanical energy, or E equals K plus U, stays constant. Let's ground that with a model, a spring block. Its potential is U of X equals 1/2 kx squared. Draw a horizontal energy line, E. Where the line meets the curve are turning points plus or minus X max. Any region where U is greater than E is off limits. The block can't enter those areas. Start the block at rest at plus X max and let go. It oscillates between plus or minus X max. Just like in the bowling ball demo, it never passes a turning point. Doing so would require more energy than it possesses. Equilibria occur where the net force is zero. At a minimum of U, a small push increases U, and the system rolls back. This is stable equilibrium. By contrast, at a maximum of U, a tiny nudge lowers U, and the system accelerates away from the peak. This is an unstable equilibrium. If U is flat over a region, small displacements neither raise nor lower U. This is neutral equilibrium. A good example is a frictionless puck on a level track. Mini checkpoint. So far, we've defined U of X, the energy line E, turning points, and 3 types of equilibrium. Think you've got it down? Head over to this link for a practice test and join the study streak, or stick around to learn more about the topic. Back to the diagram. How fast are we moving? Its speed comes from kinetic energy. K equals E minus U of X. Where U is low, K is high, so motion is fastest. As U approaches E, K approaches zero, and the object pauses at a turning point. Before we go further, watch out for common pitfalls. First, don't confuse X with a time. Moving right on the graph doesn't mean later. Second, remember this is a potential energy diagram, not a position time plot. Third, U of X depends on the force involved. It isn't always gravitational or linear. For example, bonded atoms, a typical molecular U of R dips to a minimum. The stable equilibrium separation is at that minimum. From the sketch, it's around R approximately 3 times 10 to the minus 10 meters. That's about 0.3 nanometers. Now, for an edge case, double well. If E lies below the central barrier, motion is trapped in one well. However, if E rises above the barrier, the particle can move between wells and explore both regions. Let's practice the moves. Given U of X and a line at E, identify turning points A and B, mark the allowed region, and remember, motion is fastest where U is lowest. Finally, classify labeled points. A minimum means stable equilibrium. A maximum means unstable equilibrium. To wrap up, read U of X, like terrain, valleys trap, peaks repel, plateaus allow drifting. The energy line E sets boundaries. Turning points mark reversals, and speed comes from the gap between E and U. Ready to quiz yourself with the content covered in this video? Check out the link in the description where you'll find Quizlet content made just for you.